So, in this lecture, we will discuss conditional convergence and ratio test for absolute convergence. So, let us recall what is absolute convergence. So, for example, consider a series 1 minus 1 by 2 minus 1 by 2 square plus 1 by 2 cube, etc. This series is not alternating series. This series is not alternating series. Why? Because this is not alternate terms are not positive and negative. So here second term is negative and third term is negative. So this is not alternating series. So we cannot use alternating series test. So now I define. Let us recall what is absolute convergence. A series sigma k equal to 1 to infinity uk u1 plus u2 plus etc. uk is said to converge absolutely if the series of absolute values sigma k equal to 1 to infinity mod uk, that is equal to mod u1 plus mod u2 plus etc. mod uk converges and is said to diverge absolutely if the series uh, absolutely if the series of absolute value diverges. So diverge absolutely means series of absolute values diverges. Now there is an important theorem. Theorem is very important because the theorem states that if the series sigma k equal to 1 to infinity mod uk is equal to mod u1 plus mod u2 plus etc. mod uk plus etc. That means absolute values of uk converges if the absolute values of the series uk converges, then does the series sigma k equal to 1 to infinity uk equal to u1 plus u2 plus etc. uk plus etc. converges. That means if a series sigma uk mod sigma uk converges implies sigma uk converges. That means if a series is absolutely convergent, then the series converges. Now I will ask a question. Does series sigma uk converge implies sigma mod uk converges? Is my question. That means if a series converges, does it imply series absolutely convergent? So from this theorem we get if series is absolutely convergent, then the series is convergent. If the mode values converges, then the original series is convergent. My question is, does UK, that means sigma UK converges, does it imply its modulus value converges? So this is our question. The answer is no, because if you take an example, we know that sigma k equal to 1 to infinity minus 1 power k plus 1 into 1 by k. So this is an alternating series, and by alternating series test we already showed that this series converges. So the original series is sigma k equal to 1 to infinity minus 1 power k plus 1 into k. Now if we take absolute values, sigma k equal to 1 to infinity modulus of minus 1 power k plus 1 into 1 by k. So this series is actually, if you take mod, then negative terms will cancel. So 1 by k. But this series diverges. So that means if the series implies series is convergent doesn't imply series is absolutely convergent. So this example, this series converges, but its absolute value doesn't converge. So our theorem shows that theorem tells us if a series absolutely convergent, that means modulus values convergent, then the series also converge. So now we want to do these two problems. Show that the following series converge. So given series is the first one solution. Given series is 1 minus 1 by 2 minus 1 by 2 square plus 1 by 2 cube plus 1 by 2 raised to 4 minus etc. Now this series is not alternating series, right? 1 minus 1 by 2 minus 1 by 2 square plus etc. So we know the theorem. The theorem tells us if a series is absolutely convergent, then the series is convergent. So in order to prove this series is convergent, it's enough to show that the series is absolutely convergent. It's enough to show that the series is absolutely convergent. So the absolute values of the absolute values of given series is, so the absolute values of given series is 1 by 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus etc. So this series converges because it's a geometric series. Geometric series with r equal to 1 by 2. So r less than 1, therefore the series converges. So this series converges, that means series of absolute values convergent. Therefore by this theorem, we can say that the series 1 minus 1 by 2 minus 1 by 2 square plus 1 by 2 cube plus 1 by 2 raised to 4 converges. Okay, have you got it? Any doubt? If you have any doubt, you can ask me. So, in order to prove this series is convergent, we just take its absolute value and we showed that that is absolutely convergent. So, we will do next problem. So, this is another important problem. We show that this series converges. Sigma k equal to 1 to infinity cos k divided by k square. Now take so now I am taking the absolute value k equal to 1 to infinity mod cos k divided by cos square. So we know that what is the value of cos is always less than cos k is always less than mod cos k is always less than or equal to 1. That means we know that value of cos theta is always, cos k is always in between minus 1, 1 and 1. Therefore, for any value, mod cos k is less than or equal to 1. Therefore, we have here mod cos k by k square. Thus, therefore, we have mod cos k divided by k square is always less than or equal to 1 by k square. So this series is 1 by k, and we know that sigma 1 by k square converges, right, by p series test, because p is equal to 2 here. So the biggest series converges then definitely the smaller series converges. Therefore, by comparison test, sigma mod cos k divided by k square converges. Sigma mod cos k divided by k square converges. Therefore, the series of absolute value converges, which implies series k equal to 1 to infinity cos k divided by k square converges. So in order to prove these two series are convergent, we just take its absolute values and we showed that these series are absolutely convergent. So absolutely convergent doesn't imply absolutely convergent implies series convergent. Okay. Any doubt? If you have any doubt, you can ask me. So that is absolute convergence. Now, next is very important topic, conditional convergence. I told you that a series convergent doesn't imply it's absolutely convergent, right? A series UK converges. This doesn't imply sigma mod UK converges, right? So such series are called conditionally convergent series. So a series sigma UK is said to be conditionally convergent if if sigma UK k equal to 1 to infinity converges, but sigma k equal to 1 to infinity its modulus value UK diverges. That means a conditionally convergent series is a series that converges but diverges absolutely. For example, I told you one example. If you take sigma k equal to 1 to infinity minus 1 power k plus 1 divided by k. This converges, but sigma mod minus 1 power k plus 1 by k diverges. So this is an example for conditionally convergent series. So this series is an example for conditionally convergent series. Now I will give you another example. If you take this series, sigma k equal to 1 to infinity minus 1 power k plus 1, k plus 3 divided by k into k plus 3. So we already shown in last class that this series converges by alternating series test. Converges by alternating series test. Okay, so this series converges by alternating series test. Now we will show that we will test its absolute convergence. For example, so I'm taking the absolute value sigma k equal to 1 to infinity mod minus 1 power k plus 1 k plus 3 divided by k into k plus 3. So this is actually equal to sigma k equal to 1 to infinity k plus 3 divided by k into k plus 1. Now we want to prove that this series is divergent. So this suggests the series of absolute values should behave like divergent. So in order to prove that, we will use limit comparison test. So I am taking AK. My AK is this k plus 3 divided by k into k plus 1. And BK, I am taking BK is 1 by k. So we know that what is limit comparison test. Rho is equal to limit k tends to infinity ak by bk. So So this is limit k tends to infinity ak. Ak is actually k plus 3 divided by k into k plus 1 into 1 by divided by 1 by k means into k. So that is this. So this and this get cancelled, and the limit is 1. So rho is 1, that is finite. Therefore, both the series behaves like same by limit comparison test. Right. So by limit comparison test, this series is absolutely divergent. So the absolute values of this series is divergent. Therefore, this series is conditionally converges conditionally. Okay. So that is another example. Now my question is so we already showed that a series is conditionally uh, not absolutely convergent. This series may converge or diverge. Does there exist any test to check whether the series is absolutely not absolutely convergent implies series diverges? അതായത് if നമുക്കൊരു series തന്നതിന് if it is not absolutely convergent, then does we conclude that that series is divergent by using any other test? So there is an important test called ratio test. You already studied ratio test, but this test has some importance. Why? Because we can check the absolute convergence of. So ratio, ratio test for absolute convergence. So you already know that what is ratio test. Ratio test for absolutely convergent. Sigma mod sigma UK converge be a series with non-zero terms. So here you can use non-zero terms. Suppose that rho equal to limit k tends to infinity mod UK plus 1 divided by mod UK. So instead of using any ratio, the previous ratio test, we can use this ratio test for calculating or for checking whether the series is convergent. So here rho is equal to limit k tends to infinity mod UK plus 1 divided by mod UK. If rho less than 1, then the series UK converges absolutely, therefore converges. So if rho less than 1, the series is convergent absolutely, therefore series is convergent. And this is the important part. If rho greater than 1, then the series is divergent. It's not only absolutely divergent, but the series itself divergent. Okay. So rho less than 1, series converges absolutely, therefore series converges. Rho greater than 1, series diverges. So now we will if rho equal to 1, there is no conclusion, right? So now we will use ratio test for absolute convergence, whether the series is convergent. So first we will take limit sigma k equal to 1 to infinity minus 1 power k 2 raised to k divided by k factorial. So this is actually there is negative terms. So in order to check whether it is convergent, absolutely convergent or not, we will use ratio test. So taking absolute values uk, we obtain mod uk is equal to modulus of minus 1 power k 2 raised to k factorial, that is equal to 2 raised to k factorial. If you take rho is equal to limit k tends to infinity uk plus 1 divided by uk is equal to limit k tends to infinity 2 raised to k plus 1 divided by k plus 1 factorial into reciprocal of uk, that is mod uk, k factorial divided by 2 raised to k. So now If we cancel out this, we will get 2, and if we cancel out this, we will get k plus 1. As limit k tends to infinity, this goes to 0 and less than 1. Therefore, the series converges absolutely. Therefore, it is convergent by ratio test. By ratio test, the series is convergent. Now we will check out the second series. Sigma k equal to 1 to infinity minus 1 power k 2k minus 1 factorial divided by 3k. So for that, I am taking absolute value mod uk modulus of minus 1 power k 2k minus 1 factorial 3 raised to k, which is equal to 2k minus 1 factorial 3 raised to k, rho equal to limit k tends to infinity uk plus 1 divided by mod uk, which is equal to limit k tends to infinity 2k plus 1 minus 1 factorial divided by 3k 3 raised to k plus 1 into, we will take the reciprocal of uk into 3 raised to k divided by 2k minus 1 factorial. So if you cancel it out, you will get 1 by 3 is there, 1 by 3, 2k plus 1 factorial divided by 2k minus 1 factorial. Okay. So this is limit k tends to infinity. You can cancel out it here. You will get 2k, 2k plus 1. This is plus infinity. So if rho is greater than 1 or plus infinity, the series diverges. So by ratio test, we can directly say that this series is not only absolutely divergent, but also it is divergent. Series is divergent. So now you can use ratio test for checking whether the series is divergent or not. Now we will check it out a few problems. These are the exercise problems. You can do this problem. So we can do this problem.